Thank you very much for coming out today. It's such a wonderful day that I'm very pleased that anybody has managed to turn up at all. So what I want to do is talk to you a bit about the brain, talk a bit about what we know about how it works, and I want to challenge you a little. I'm going to do some practicals on you in the latter half of the talk. I hope you've all washed your hands for one of them. That's a clue. What do you want to know about the brain? Well, you don't need to know very much, actually. The first thing to know is that the brain is like any other tissue in the body. It's composed of cells. These cells are given the specialized name of neurons, and these neurons talk to each other. They communicate with each other. They form networks for processing of information. And that's what you have represented over here. These are neurons known as pyramidal cells because the shape of the cell body here, if you squint, is a little bit like a pyramid. And if you rotate it in three-dimensional space, it actually does look like a pyramid. Now, what do brain cells do? Well, it hopefully will come as a surprise to you, but brain cells are actually quite stupid, believe it or not. They do, in principle, very little. They either talk to the cell that they're communicating with, or they don't. That's it. The message that they send on is either to fire or not to fire. And that's very, very simple. Now, the underlying physiology is complicated. We don't need to worry about that here today. But the simple principle that cells either talk to each other or they don't, they tell other cells to fire or they tell them not to fire, is really all that you need to know, except for one property. When these signals pass from one cell to another, they cause changes in other cells. And this is the property that we refer to as plasticity. So brain cells are plastic. They're quite unlike other cells in the body because they have this property. This, for example, is actually a famous slide of the development of the frontal cortex in a rat. And you can see here in a newborn rat, you've got very little by way of connections between brain cells. But by 24 months old, which is very old indeed for a rat would maybe live to about 30 months, you can see how the cells are really extensively ramified and talking to each other in a very, very profound way. And that's an experience-dependent thing. It happens because of experience, but it also happens because of maturation, nutrition, and a whole lot of other things. Okay, so what's the point? The point is this, that the brain changes because of experience. Our behaviors, our attitudes, the way we talk to ourselves, all of these things all have a profound effect on the plasticity of the brain. To put it another way, the brain can change itself simply because of its own activity. Now, this is a slide I always love. This is a CT scan through the body, and you have the brain up here at the top, heart over here, liver at on the side. And this plots approximately the energy use of the brain at a moment in time. And what you see, it should be obvious to you, is that the brain is very busy compared with every other part of the body. In fact, it consumes about 20% of the energy output of the heart. And again, this should be obvious to you if you think about it for a moment. If you interrupt the blood supply to the heart, and if you look carefully here, you'll actually see one of the major blood vessels coming up to the brain. If you interrupt that for just a few seconds, you'll lose consciousness. The brain has no energy stores. Glucose, oxygen, all of those things have to be carried into the brain, and waste products have to be taken away from the brain. So the brain is very, very physiologically active. And this means that the brain never, ever rests, not even during sleep. You might be unconscious during sleep, but your brain is definitively not resting during sleep. Just to give you a simple example of that, about 80% of the growth hormone that you excrete as a child happens during the 20 hours that you're asleep as a newborn. It doesn't happen during waking, it happens actually during sleeping. But again, the key point is the brain is always hungry. It's hungry for glucose, it's hungry for oxygen, but it's also hungry for stimulation. And a lot of that stimulation is stimulation it provides itself. And it does that by way of the way we talk to ourselves, among other things. So this is an interesting concept in neuroscience I want to introduce you to. It's the idea of a mindset. And we do all engage in conversations with ourselves. We tell ourselves what we're good at, what we're bad at, those kinds of things. And it's possible to distinguish two different mindsets. One we refer to by the phrase a growth mindset, and the other we refer to as a fixed mindset. Now, a growth mindset takes the view that failure is a challenge and that you can develop your intelligence, you can develop your talents, and that the limits you place on yourself are just that, limits that you place on yourself. Whereas a fixed mindset, characteristically people with a fixed mindset will say, I'm not a creative person, or very commonly these days, I'm not a maths person, or something like that. And that's not true. Everybody can count, or at least everybody with a normal brain can count. So you can learn some maths. You mightn't be an Einstein with the maths, but you can certainly get better at maths. And this is the idea that how you talk to yourself is very, very important, but also how other people talk to you. Teachers reinforcing one message in school versus another can have a very profound effect on development. Or indeed, so can parents. This is Homer, I'm sure you all know him. The message here is, you tried your best and you failed miserably, and the message is never try. Now, let's just think about this for a moment, because Carol Dweck, whose work I'm talking about here, distinguishes ways of inducing mindsets. And there are several ways of doing this. One is to focus on how smart somebody is. You've done very well because you're very intelligent. A better way of approaching this is to say to somebody, you've done very well because you've worked very hard. And the last way is to just say, this is a really good score. This is in terms of a school intervention in a minority school in Los Angeles. And this is what she finds. In terms of maths performance, if you divide children, or teenagers as it is in this case, into two groups, and you focus on telling one group that they're getting better because they've worked hard, and you focus on the other group, or you tell the other group that they're getting better only because they're intelligent, what you find is the group that you've told that are getting better because they work rise to the challenge, and their maths performance rises over time. And she's shown this in children as young as 4, and she's shown it in university students and also in sports performers in a wide variety of backgrounds. The simple intervention that asks people to focus on what they're doing rather than what they are has a profound effect on people's behavior. Now, what happens in the brain? Well, we can measure brain waves very easily. We attach a cap to your skull. These measure electrical activity in the brain, and you get these kinds of activity that you can see up here on the top left. Now, this is a difficult task. This is called a flanker task. So you get presented with a stream of letters, and you're asked, is the letter to the end the same as the letter in the middle? And you have to do this very quickly. So it's tap, 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 tap. All you do is you tell your subjects at the start, this is a task you can't get better at, or you tell them it's a task that you will get better at. Look what happens. You get much greater engagement in the group that are told they can get better over time. Their performance gets better over time, as measured down here, and you can see much more brain activity in that group compared to the group that are told they can't get better, that this is a task that you're fixed at. That's how simple the intervention is and how profound the effect can be when you actually look at activity in the brain itself. So, what's the point here? The point really is very simple and straightforward, that how we talk to ourselves, how we represent ourselves to ourselves, and how others talk to us about our own abilities has a big effect on how we perform in life. And what we should do is focus not on how smart we are or those kinds of things. What we should be doing is focusing on how hard we're working and how we can learn from failure. Okay, so that's an example of a positive form of plasticity. Now I'm going to ask you to raise your hand. Without hitting you over the head, can I reduce your IQ reversibly by 15 points? Who would say yes? Who would say no? Okay, yes, good. Well, it's really easy. That's how I do it. Keep you up all night, and if I test you in the morning, I'll find on average your IQ has gone down by about 15 points. Now, it'll come back a little over the next couple of hours, but the key point to get across here is that sleep hygiene in the West in particular stinks. We do not understand how important sleep is for cognitive function. Now, just to underscore the point, this is a curve showing you what proportion of the population, the IQs of the population at large. The average person has an IQ of 100, so it's set to be 100, which is that point there. So if you're down 15 points, you're dropping into the lowest 13.5% of the population, which is not good. So take a good night's sleep and do that regularly. Okay, so let's talk about something else. So what I want to do now is just talk about what happens when we talk to each other. Now, if you listen into people talking about, or just having conversations out in cafes or pubs or whatever, and you count what they're saying to each other. What you find is that about 40%, on average, of what people tell each other is personal disclosure. They're talking about themselves. And that's irrespective of whether you're male or female. There's no sex difference here. And there's a natural question. Why do we do this? Why do we talk about ourselves? Well, here's why, potentially. If you get people and you put them in a brain scanner and we ask them to do simple acts of self-disclosure, talk about when they were born, where they lived, those kinds of things, who they were friends with in school, nothing particularly private, or to talk about facts that are known about public people. What color is Bertie Ahern's hair? This structure in the brain, the nucleus accumbens, deep in the center of the brain, which is the core of the brain's reward system, is activated when you're talking about yourself, but it's not activated that much when you're talking about other people. So you want to know why we like talking about ourselves? It's intrinsically rewarding. Now, how rewarding is it? It's rewarding to the point that people are, you don't need to go through the detail here, people are willing to pay a monetary cost in terms of the reduction in the fee that they will get for participating in the experiment in order to continue talking about themselves. Because we find talking about ourselves intrinsically rewarding. So, takeaway point here really is very simple. Humans like to gossip. We like to gossip about ourselves. Shouldn't be a surprise. But we do it because it activates our own brain's reward system. Now, for those of you who are managers here, there's a very important lesson here. A good manager should know how to listen. You shouldn't be talking. You should be letting the person that's in there talking to you talk so you can hear what they have to say. They're going to enjoy engaging in the act of self-disclosure anyway, so you may as well just let them get on with it. Okay, so memory and the brain. Who's seen this before? Who knows what this is? You all think it's the Mona Lisa, don't you? Some of you do, some of you don't. I've got a shaking head, which is good. That's actually the Mona Lisa. Good. The last time I did this, it was in a very large audience, maybe 300 people or something, and 2 people spotted that it was the wrong way round. So the point here is that you've seen this image many, many times, but you can't actually remember which one it is. That's not true for everybody, but it's true for many people. But for the people who were very clever and spotted the one before, who has handled a 20-euro note today? In the last week? Now tell me what it looks like. Okay, it's blue. It's got 20 on it. Now, what else? Okay, so that's what it looks like. If you say there are bridges on it, people will remember that there are bridges, not church windows. If you say there are other structures, people will remember other structures. There's even a dome there. Point here is that you're exposed to these stimuli lots in everyday life, and we don't remember what they are. Now, I'm sure you know what this company is. It's Apple. Now, which one of these is the company's logo? Which of you are Apple users? Okay, so good challenge there. Something that you're exposed to, that you work in front of a lot. We know the company is worth, what is it, 500 billion or whatever enormous number it is. Some say it's going to be the first $1 trillion company. And we can't remember what its logo is. Okay, so if we ask you to do things, to draw the logo and rate your recall, and we do it on the basis of whether you use a Mac or you use a PC or you engage in mixed use, this is what you get. Even for Apple users, the recall might be high, but their confidence might be very low. It's not good. So what you find is that people's recall is very, very poor for everyday objects. Now, that's the actual logo over there on the bottom right. How many people knew that? Yeah, okay, so not so many. So the point here is that just because something is familiar doesn't mean that it's been learned. And we can think of lots of explanations for why that might be the case. Attentional saturation is one. You've learned that the phenomenon is irrelevant or whatever. But the point is that just because you've learned it, you think you've learned it or you've been exposed to it, doesn't mean that you actually do recall it particularly well. Now, did I show you that image before? No, I didn't. I showed you that one. Gotcha. Okay, so this is a forgetting curve. It's the very first one that was ever plotted more than 100 years ago by Hermann Ebbinghaus. And what he shows, depressingly, is that when you're given material to recall and you're tested over a period of 31 days, that you remember about 20% of it after 31 days. And I think advertisers have a similar problem. These are US data, but on average, people are exposed to somewhere perhaps around 600 adverts per day. And many of these come through traditional media. And people aren't very good at remembering what they're being exposed to. Now, there are all sorts of reasons for this, but I think one of the possible reasons is the memory system of the brain is actually quite complex, and you have to engage it in a very defined set of ways. And typically what we think is that we can break memory down into at least 3 processes. One where you have to encode the information, a second one where you have to consolidate it. It has to be stored in the various networks of the brain. And then finally, you have to retrieve it, which is the last phase of memory. And I think advertisers focus a lot on this, and they don't think about these other latter processes. Okay, so your gag reflex. Anybody here ever got sick? Everybody has. You just don't remember it. When you were a kid, you did it. Now, we can get sick very easily. Buccal cavity is very sensitive, and if you touch this surface, you will gag. So, what I want you to do, a little distasteful, is take your right index finger and put your finger in your mouth and just feel where your gag reflex is. Please. This is worthwhile. Just don't do it to the point of throwing up. Okay, if you all found your gag reflex, now, do you think, can you control that reflex? Okay, so their head's being shaken, which is good. Actually, you can control that reflex, and I want to teach you how. So, take your left hand, put your thumb across your hand. Now squeeze that really hard to the point that it hurts. And drop your hand. Now put your finger back in your mouth. Oh, it's gone. How did that happen? Well, this is why it may happen. This is the sensory surface in the buccal cavity. You touch that, and you get a single impulse that runs through the spinal cord, back to the muscle, and you go, you want to heave. But when you're doing this, there's competition in the brain, and as we'll see in a moment, there's much more brain given over to your hands than there is to the buccal cavity, to this portion of the mouth. So there's a simple act of competition, and one beats the other. So if you have a kid and you can't get them to swallow a pill because they're complaining that they're choking, this is a really good trick. If you think you're going to heave yourself when you're in the dentist, again, this will work very, very well for you. Okay, so that's a reflex. And it just shows you that with the thinking about it in the right way, we can get a reflex under conscious control. Now, the number 6. Just everybody do this. Just make a number 6 in the air with your right hand. Great, okay, very simple. Now, how did you do that? Well, you did it because you've got activity here in the motor strip, sends a command down the spinal cord, out to your fingers, okay, through the medial and lateral lemniscal nuclei, down through all that stuff. You don't need to worry about the detail of it. Now, take your right foot and turn it out clockwise. Okay, really simple. Now, do the number 6 and turn your foot out. You're not turning, you're making the number 6. No, that's how you do it. Turn your right foot clockwise and make the number 6 with your hand at the same time. Seen what's happened? Yeah. Now, why did that happen? It happened for this reason. This is the motor strip. This is the amount of the brain that's given over to your foot. Not very much at all. This is the amount of brain that's given over to your hand. Our hands are almost what define us as humans, because we have such a dramatic overrepresentation of the hands in the brain. This is called the motor homunculus. It's the little man or the little woman on your brain. We were talking about the tongue earlier on and gagging. That's it. Very little. Look how much is given over to the thumb. Massive amount of brain given over to the thumb. So the simple competition, this little small signal down here has to compete with this massive signal up here, and it loses. So there's a voluntary movement, and you can't control it. And we have a gag reflex, an involuntary reaction, and you can control it. Okay, speech and hearing. So I'm just going to talk very quickly about speech. This is Paul Broca. He's a French neurologist from the 1800s. And he studied many patients during the Napoleonic Wars. And one of the disadvantages of being shot in the head during Napoleonic times is that you typically or often didn't die because you were shot with a low-velocity musket ball. And Broca showed that in right-handed patients who were shot in the left temple in a circumscribed area, that they would selectively lose the ability to speak, but not the ability to understand language. They could write language and they could follow commands, but they were no longer able to speak. And that was, I think, one of the very first really important discoveries in brain science, that you could localize a particular function to a particular area. And notice the important point here. It was the active speech. So this is a motor speech area. It's not a speech comprehension area. That's actually up here, Wernicke's area, and I'm not going to talk about it today. Now, how do we hear? Hearing is very simple, we think. We do it all the time. This is the outer ear. Sound passes here into the cochlea, and you can unfold the cochlea, and effectively, the best way to think about it is like a piano with bass keys and at one end. And the sound passes through here, and the auditory nerve takes it into the brain. Now, what actually happens in the brain, or sorry, in the cochlea, is you have these hairs growing in there that swing around, and they move according to the strength of the sound that they're being exposed to. So there's an individual hair cell, and these sample different parts of the sound spectrum. So I'll give you an example of how that works now. So hopefully this will work. This is a single hair cell.
1, 2, 3 o'clock, 4 o'clock, rock.
Now, can you see this?
5, 6, 7 o'clock, 8 o'clock, rock. 9, 10, 11 o'clock, 12 o'clock, rock. We're gonna rock around the clock tonight. Put your glad rags on. Join me home. We'll have some fun when the clock strikes 1. We're gonna rock around the clock tonight. We're gonna rock, rock, rock till broad daylight. We're gonna rock around the clock tonight.
So this is called a dancing hair cell, and this is harvested from the inner ear. This is a microelectrode sitting at the bottom, and this moves according to the sound that it's hearing. It only moves for certain sounds and not for others. And because it moves in a particular way, in a particular reliable fashion, it transmits electrical signals, and those signals go to the brain. And in this case, it likes all the bass notes in Bill Haley's Rock Around the Clock. Okay, now, different question. The Nobel Prize was given just before Christmas to an Irish-American, John O'Keefe, from Cork. Sorry, his family is from Cork and from Mayo. And he spent his life dedicated to understanding how it is that we know where we are, or how the brain knows this, and how we know where we're going. And this is an example of how it is that we know where we're going. It's called a head direction cell. So what he's been doing, and other labs have been doing, is recording the activity of brain cells in animals while they navigate in a simple environment. So hopefully you'll be able to understand when you look at this exactly what this cell is responding to. So here we have a little rat running around, and occasionally you'll see a food pellet being thrown in there, and you don't hear anything much, background noise. Did you hear that? That's the heading sense, or heading portion of the brain's GPS system that tells you where you're oriented in space. And this cell only fires when the animal is looking in this direction in space. And when he turns his head away, it stops. So it's now known that there's a complex network of areas in the brain that are responsible for your orientation in space. And damage to these areas, which are also intimately involved in memory, is thought at least to be part of the reason why your sense of orientation in space and time is lost with certain types of head injury, with certain infections, and also with certain dementias. Okay, I'm going to just summarize in 2 quick lessons. I think growth mindsets are really easy to learn. You have to get used to telling yourself that failure is okay, but it has a profound effect on performance, and they are actually a very easy trick to learn. But I think even more important than that, if I could send you away with this message, the best cognitive enhancer we have, apart from aerobic exercise, is a regular night's sleep. People cut their sleep down regularly, and it's not a good idea. But sleep works better than any drug that's available for the enhancement of cognition. There is absolutely no doubt about that. The other thing that's obviously very good for your brain as well, and for your heart, is regular aerobic exercise, but that's another day's discussion. Okay, I'll stop there. Thank you.